We're ready to move right on now into 19.2, and we'll take a look at our first type of root finding or method of finding roots of an equation. And I wanted to start off with an example so that you see graphically what it is we're trying to find. Consider the function f of x, which is defined here as x to the fourth minus x minus 10. If we plotted that, and here I've just used Excel to make a really quick plot, you can see that it crosses the x-axis at a number somewhere between minus 1 and minus 2, and it crosses again somewhere between 1 and 2. And those are the only roots, the only times it crosses the x-axis. And what we want is some method of finding exactly what the values are, what the values of x are when it crosses that axis. To do that with the method known as fixed point iteration, what we need to do is we need to rearrange the function f of x so that it has some form that has x to the left, and then we have g of x to the right. So we just rearrange the f of x equals 0 expression of the function and create another form. Let me show you an example or two. First, we'll try taking our f of x equals 0 and we rewrite it. And here you'll see that I took 10 to the right side, then I took x out of the remaining numbers on the left, and then rearranged it so that I had x equals 10 over the quantity x to the 3 minus 1. So with this version, I have a sample g of x on the right, where x equals g of x is the kind of rearrangement that I got to. Let's see if I can use this. What I'll do is I'll make a guess of a value of x, stick it in on the right side of that equation at the bottom left, and I'll calculate a new x using this expression. And then I'll try that x over on the right. And if I go through a couple cycles of these, we may or may not get one of these roots. Let's see how we do with this particular formulation of g of x. For this formulation of g of x, I'll make an initial guess of my root as 2, and we'll see what happens. When I stick in an x of 2 on the right side of the equation, I calculate a g of x, or my next guess for x, at 1.42. That's my first iteration. When I use that on the right, that would calculate a new g of x of 5.22, which is getting further away from the root, which we know is between 1 and 2. So you can see with this formulation of g of x, I'll eventually, when I go from one iteration to the next, I'll bounce back and forth between a number very close to 0 and a number very close to minus 10. And I'm not zeroing in on the root that I was looking for. I'm just bouncing around in values of x. So I haven't converged to the solution. So this formulation did not work. But I could have rearranged the expression so that I had a different formulation of g of x, and it might work in different reformulations. In fact, if I had rearranged to the formulation x equals g of x equals the quantity x plus 10 raised to the 1/4, then I repeat this initial guess of x2 with this formulation. After one iteration, I'm really close to my root. After a second iteration, I'm pretty much there, and I stay stuck there. So as I move from sticking the next value, the value of x that I just calculated in as my next guess, I very quickly converge to the exact, or as close as I'm going to be able to get to the answer for what's the root of this function. So that's the fixed point iteration. If it seems like it's a little weird that it sometimes works and sometimes doesn't, and you have to get lucky, that is a valid way to see the fixed point iteration. Some particular applications have enough repeatability, that they know that they can use this if they make their formulations of a particular structure. But in general, this is not a reliable method, but it's one of the first ones that people commonly learn, and it might be something you're accustomed to, and then again, it may not be. I never use this method, but in case you have seen it or want to use it again, your book covers it, so I included coverage of the fixed point iteration. It turns out that if you look at your g of x formulation, so you've just rearranged f of x equals 0 into some form that is of the type x equals some function g of x, and that you get from rearranging f, it turns out that if you take the first derivative of g, so if you take the derivative of that new function, if that derivative is less than 1, the absolute value is less than 1, then it will converge to a root. And not necessarily the root you were looking for, but it will converge to a root. So there's our convergence test. We just have to have a slope that's very small in our formulation for g. There's a more reliable method that maybe you learned in calculus, and that's the Newton method or the Newton-Raphson method. This method requires that we be able to take the slope of our function, and you'll see that in this form we just iterate from one guess of x that is our root to the next guess of our root with the expression our next guess, x of n plus 1, is equal to our earlier guessed x of n minus the value of the function at x divided by the slope at x of n, or f of x over f prime of x. So let me explain this graphically. If we have some function that's going to cross our x-axis, what we want is to know the value of x where it's crossing the x-axis. How we get to it is we make some initial guess at the root, and then we use the value of the function at that x and the slope that we can calculate at that value of x of n, and then we slide the slope back to the x-axis and use that new value of x of n as our next guess at the root. And you can see, I hope you can see graphically, that this will get us really close to the root very quickly. In fact, the Newton-Raphson method is well known for being excellent at being a reliable converger. In the type of example that I wanted to cover here, with the same expression that we looked at in fixed point iteration, we'll now look at Newton-Raphson method or Newton method, and you can see that we can, in about 3 or 4 iterations, we can zero into the value that we're looking for. So we get right to the root really fast with just a few iterations of the Newton-Raphson method or the Newton method.